Thank you everybody for coming, listening my talk today. So the goal of my talk today is to share with you some ideas to the best of my understanding on this recent preprint, Federated Learning on Riemannian Manifolds by Li and Ma, that was uploaded to arXiv quite recently, like less than 2 months ago. So the contributions of this new preprint are algorithms for federated learning with non-convex constraints. So these authors claim that, according to their knowledge, problems in federated learning with non-convex constraints have not yet been considered. So they propose a new algorithm called Riemannian Federated SVRG. So SVRG is an existing algorithm, so we will see later in the talk. And they add, let's say, the Riemannian tools to extend it to Riemannian manifolds. And they also give some theoretical results about convergence of their algorithms, of the algorithm for different scenarios. So in my talk, I will discuss federated learning on Riemannian manifolds and the applications of federated KPCA and classical PCA. I will present some fundamental ideas and tools on how to do optimization on Riemannian manifolds. And I will give particular emphasis to the algorithmic components of these newly proposed algorithms, and we will see them later. And finally, we will discuss some numerical experiments on synthetic and real data. So if you have any question, I forgot to say, you can interrupt me also during the talk. Please don't hesitate. So let's start with an introduction to federated learning. So the classical federated learning problem aims at solving this optimization problem here, where the function f of x is a function of a variable, of a vector variable in Rd, and f of x is defined as the average over n local agents of some local loss functions, this fi of x. Okay, so each loss function is stored in a different local client or agent, Li, which are depicted here for I going from 1 to n. Okay, so these local agents can have different physical location and different hardwares. And we have, so in federated learning, then we have a central server that collects the information coming from the local servers and aggregates this information and outputs a consensus that minimizes the sum of the loss functions from all these clients. So the aim of federated learning is to use computational resources of the different clients while maintaining data privacy between while maintaining data privacy, because in fact the local clients never communicate between themselves, but they only communicate with the central server. And let's say, how does the problem look on a Riemannian manifold? Well, at the first glance, it's basically the same. What changes is the fact that now the optimization variable is constrained to a manifold. So a manifold, for the purpose of this talk, you can really think of it as a two-dimensional surface in three-dimensional space. Of course, not in all the cases it's something so simple, but I think it's a good idea to, it's a good picture to fix our ideas on, to have some concrete object that we can visualize in our head. So I will use some images like this all along the presentation, all throughout the presentation. So the mathematical expression looks the same as I was saying, but the variable is constrained to a manifold. So now the local loss functions are functions from the manifold to R, okay? And we'll see some Riemannian manifold concrete example later. So in the context of federated learning on Riemannian manifolds, the authors consider two practical problems. The first one is the federated KPCA problem, namely this one. So again, f of x looks the same, but now we have a specific instance of a Riemannian manifold, which is the Stiefel manifold. So for the moment, let's just say that this is the set of orthonormal matrices in R, D times R. And later I will say something more about this manifold. So yeah, we have a concrete instance here, and then and also a concrete instance of the local loss functions. So they are given by minus 1/2 the trace of x transpose AIX, where x is the optimization variable, and AI is the covariant matrix of the data xi, which are stored in the ith local agent. Okay. And then, well, actually, I said, okay, they consider two applications, but the second one is basically a special case of the federated KPCA. So in the special case where R, the R here in the Stiefel, one of the two parameters in the Stiefel manifold, is equal to 1, we get the classical PCA. In this case, a Stiefel manifold coincides with a unit hypersphere embedded in RD. Okay. So it has just this expression. So the points of the unit sphere, yeah, I mean, just have norm, unitary norm. Okay. So the local loss function expression simplifies to this expression. So again, the reason for considering these algorithms is given by the difficulty in classical federated learning problems to aggregate points over non-convex sets. So while here in the framework of Riemannian optimization, we can consider the constraints explicitly. So by exploiting the geometric structure of these constraints. So they really have the structure of a manifold. Do you have any questions so far? Okay, if there are no questions. Okay, so more precisely, the contributions of this paper are this algorithm, so Riemannian Federated SVRG algorithm, which is the extension to manifold of an existing algorithm called Federated SVRG of 2016, and the convergence rate of big O 1 over epsilon square for obtaining an epsilon stationary point where epsilon is a small tolerance. So the authors claim that this is the first algorithm for solving federated learning problems over Riemannian manifolds with convergence guarantees. And the main novelty of their approach is a consensus step. So we will see later what this means more precisely. So the consensus step, let's say the step in which we aggregate the data, the information coming from the local clients, the consensus step is based on is performed on the tangent space to the manifold. Differently from the classical, let's say, the widespread used approach, which is based on the so-called Kerr-Mean approach, which I put on, yeah, so this term apparently the same author of the Kerr-Mean doesn't like it, because actually he wrote a note on archive, which is available on arXiv already in 2014, that researchers should not call it Kerr-Mean because this concept is just the Riemannian center of mass. So it is it's really a center of mass on Riemannian manifolds, but from a certain point on, researchers started to call it Kerr-Mean. So in the paper is called Kerker mean. In my talk, I will just call it Riemannian center of mass, and we will see later how this is computed. But it's not the approach used in this paper. And then final contributions are numerical results that show that their algorithm outperforms the straightforward extension to manifold of two existing algorithms, which are called AVG, Federated Average, and FedProx. Okay, so this is for the introduction. So let's look at some tools for performing Riemannian optimization. First of all, let's say a slightly more formal definition. So a Riemannian manifold is a manifold endowed with a smoothly varying inner product. So this inner product is called Riemannian metric, but it's not a metric in the, let's say, in the classical sense. Really, it's really an inner product. So strictly speaking, Riemannian manifold is a couple, M, where M is a manifold, and G is this Riemannian metric, this inner product. So it's a manifold with a Riemannian metric on it. And this Riemannian metric is an inner product that varies smoothly over the manifold. And specifically for implementing this type of structures in the computer, which is what we want to do in the end, we usually consider matrix manifolds. So these are manifolds that are, for example, constructed from the Euclidean space R n times p, okay, by taking either embedded submanifolds or quotient manifolds. So I will not talk about this in this talk. I will just talk about this a bit more about the Stiefel manifold, because it's a manifold I worked on, and it's a manifold used in this paper for the federated KPCA problem. And then there are other types of manifolds, but we will not see them in this talk. So only this one, the Stiefel manifold. Yeah. So as I mentioned before, the Stiefel manifold is the set of matrices with orthonormal columns. So it's just matrices. Okay, if the parameters are called D and R, so they are D by R matrices, which are orthonormal, which means X transpose X is equal to the identity matrix of size R. And then, so let's say with reference to the Stiefel manifold, we introduced this concept of tangent space to M at X, and also we can really visualize it as a tangent plane to the manifold at a given matrix at a given point. We can see the matrix as a point of the manifold at a given point X. So this tangent space is just the set of all tangent vectors to a manifold at a given point. It is denoted by Tx calligraphic M. And for the Stiefel manifold has this explicit expression. Okay, so it's not really important for the rest of the talk, but it's just for telling you, okay, there are, for given instances of manifolds, we can have explicit expression, and they are matrix expressions. So all the terms here are matrices. Xi is a generic tangent vector, and it is a D times R real matrix, okay, which satisfies this constraint, let's say, this equation. Okay, so you can keep in mind this picture for the concept of tangent space and tangent vectors. Do you? Yeah.
Even say it's defined by this, right? Say given
the tangent space.
Yeah. Can you find? Is there an effective way to describe this? I mean, it's described like a.
So yeah.
But is there like
okay, if I understand correctly your question, so this is a definition, but there is also an alternative characterization, let's say, in which we really have an explicit expression for the tangent vector Xi. I put it in the bonus material, so maybe at the end of the talk I can also show the alternative expression. Yeah. Okay, other questions? Yes.
Kind of an inner product on the tangent.
Sorry?
Inner product
Yeah.
on the tangent.
It's on the yeah.
You use the Euclidean or another one is called canonical.
Yeah, there are these two possibilities, right?
In this paper.
In this paper, I think they use the Euclidean, but actually it's not mentioned in the paper as far as I remember.
It would be more natural to use the canonical one, right?
Yeah, in general, yes. So, like, in my research, I use the canonical for other works I did because, so okay, this is a bit technical. So when you look at the Euclidean inner product, basically you are considering twice a certain term that appears in the structure of a tangent vector.
But in this paper, they did not say. They did
No.
not specifically.
No, yeah, yeah. Thanks. Other questions? Okay, so let's move on to two very important tools, the exponential and logarithm mapping. Given a point of the manifold and the tangent vector belonging to the tangent space at X to that manifold, the exponential mapping is defined as a mapping from the tangent space. So you can already refer to the figure here for the unit sphere. So it is defined as a mapping from the tangent space to the manifold. So like in the case of the sphere of S2, so the exponential mapping takes the vector xi and it maps it to a point which I call y on the manifold. Okay, and this point, so this point, it lies on the geodesic called gamma. The geodesic emanating from X in the direction of psi. Okay, what I just said, mathematically it is expressed by this. Okay, so the geodesic evaluated the parameter t. Okay, usually it's t. This t between 0 and 1. At 0 gives you the point X, from which the geodesic starts, and let's say the velocity of the geodesic at 0 gives you the tangent vector psi. Okay. Yeah, so these are just some, let's say, properties. So if we have a parameter t that multiplies psi, well, then and we perform the Riemannian exponential, then in that case we just have gamma of t. It is a parameter. The geodesic is parameterized according to t. That's what Jess is saying. But the very important thing is that the Riemannian distance, so the distance between x and y measured on the manifold, is between the point x and the point y, is given by the norm according to the chosen. So the norm induced by the chosen inner product, it's given by the norm. It's the norm of psi. Okay, so we have this equality. And then we have the inverse mapping for any 2 points on the manifold, x and y. If we want to compute the inverse mapping of the exponential, which is called logarithm, so it's quite a natural name, the inverse mapping at x of y is a tangent vector. And in this case, okay, so if we do the inverse mapping of y at x, we recover psi, okay? And then, okay, there are many more technical assumptions to do this kind of mappings, but I did not report them here. Okay, so, and last thing about this slide is that if we, so for the sphere, for the unit hypersphere, we have some explicit expression for the Riemannian exponential and for the Riemannian logarithm. It's not always the case. For example, for the Stiefel manifold, we do not have an explicit expression for the Riemannian logarithm. So yeah, and this has given rise to a lot of work in the numerics. So to find an algorithm that can compute this Riemannian logarithm for the Stiefel manifold, for which we do not have an explicit expression, like for the sphere. Yeah, again, the unit hypersphere is a special case of the Stiefel manifold. Okay, so it also makes sense to fix our ideas on this image in a certain sense, because it's a special case of the Stiefel manifold. Yeah.
Perhaps through the distance. So if my understanding is correct, you are defining the distance on the manifold
Yeah.
by using the tangent vector. Is that what you mentioned? The distance between x and exponential x.
Yeah, so it's this basically referring to the picture is the distance between x and y. And the distance between x and y is the norm of the tangent vector xi.
So why don't you define that on the manifold directly?
Well, this is not really a definition. This is a property. So I didn't give the definition here of the Riemannian distance, because then I mean I will have too many things to define. So I just
the property of exponential map. Because this is how the exponential map is a spatial map defined along the geodesic. So this is just if you use this as definition, then the distance between this and this will be just happen to be the tangent vector. It's used in the initial data. So this is in the because it's embedded in the geodesic equation.
yeah,
This
so
is a spatial property of
yeah, exactly. So this is really a property because
exponential map.
So
Bec-
it's a definition.
because the definition of the Riemannian distance is based on a, let's say there is a minimization problem of all the curves that connect 2 points on a manifold. So yeah, so I skipped this. So I just wanted to give this because this is something used concretely, maybe in calculation. So if I want to know the distance between 2 points on the manifold, well, I compute the logarithm mapping, and then which gives me the tangent vector xi, and then I compute the norm of xi. So this is
But this is not true in general. You have to be within the car locus, right?
exactly. So so that's why I said there are many technical conditions that I do not mention, but in general, for the type of manifolds that we consider in these problems, so like everything is nice, let's say. Yeah.
Usually this is defined locally.
Yeah, exactly.
But
Exactly.
If the
This
manifold then it can be global.
Yeah, exactly. Like the sphere or the Stiefel manifold are complete Riemannian manifolds. So yeah, let's say everything is very nice in a certain point.
So the condition that this holds is that it is a complete Riemannian manifold, is that correct?
Yeah. This is a complete Riemannian manifold. And by the way, this is also a condition. We will see later an assumption that the author of this paper used to prove the convergence result, the condition of completeness of the manifold.
As long as mentioned, this is true just for local.
For usual Riemannian manifold,
Yeah.
it's on map may not be it's defined locally, but if the manifold is good enough, then it can be global. So,
Yeah.
So you're talking
Exactly.
about, I guess in the paper they want to discuss the case where this can be applied. Because they need to use this to prove the conversion, I guess. So.
Yeah, exactly. Yes. So it's a nice setting, let's say. It's a nice situation. But yet, with the orthonormal matrices, so with the Stiefel manifold, there are many applications. So it's not so, let's say, it's a nice setting, but it's not so, so only theoretical or so detached from more concrete applications.
Can I imagine that, say, if you are working on a deep learning problem, and then we have X in somewhere, different sites, and this one can help us to define the distance
Yeah, sure.
to
Sure.
the images.
Yes.
And of course,
Yeah.
it depends on how we define the manifold, and we have different things. But
Yeah.
basically, this is what we can define distance.
Yeah, sure.
To distinguish the
To distinguish two points, let's say two objects that can be matrices, they can be vectors. Yeah.
And I guess this can be very general in the sense that can be an image, or it can be a feature space. Say we extract the feature of the image in whatever sense, that can still be a feature, a point on the feature space. So it doesn't matter what it's a really particle example. It's just a kind of R d by n space.
Sorry, if?
It can be anything
Yeah.
presented as a
Yeah.
matrix form. Okay?
Yeah, yeah. So it's, in the applications, they consider both synthetic data, so let's say artificial, in the sense that they just create some random orthonormal matrices, and then they say, okay, these are points on the Stiefel manifold, okay. But then they consider also some concrete data sets. Among them, there is the MNIST data set. I don't know exactly how to pronounce it, sorry, because I'm sure that you are more familiar with this than me. But so for the KPCA problem, so it means that these images, they can be seen as points of these manifolds. Yeah, it's really one of the examples. I will show the results at the end.
I have another question in the very beginning. So,
Yeah. Should I?
Ask that in the early, you have a minimization problem, object function is f of x, right?
This one?
Yeah. That's right. So I'm trying to connect this with some general Federated learning rules function. And assume the rules function of different Federated learning, there are different rules function. But it seems to me this is in this very special form. Can you help me to connect two things? Say if I have a different rules function, then do I need to change this f of I here, or this is just an example? Or this is for KPCA problem? I just want to clarify.
No, so as far as I understood, this is really the local loss function for the KPCA problem.
All right.
Yes.
So this is just for
So I think if you change the loss function, the local loss functions, it becomes another problem. I guess so. I mean, to the best of my understanding. So because directly, I have never worked with this KPCA. But okay, so from my point of view, it's just a. So in the context of learning now, people like to call this loss function, but for me, it's what in optimization we just call the cost function or objective function. So, I mean, yeah, it's just a mathematical function. So I don't know then, if we change it to something else, if it can be related to some other concrete application, or it's to explore, let's say. So we were, okay, so so another thing which is important in optimization is, in general, is the gradient, because usually is one of the monitored quantities in an optimization process, because when we want to, like to satisfy a first order optimality condition, we look at the norm of the gradient. So, okay, so for any embedded submanifold, the Riemannian gradient, so for any, not only the sphere of the Stiefel manifold, it's simply given by the projection onto the tangent space, which I just showed in the images before, of the Euclidean gradient. So the grad here, so grad is the notation here for the Riemannian gradient, and nabla is the notation for the Euclidean gradient, okay, just to differentiate them. For the Stiefel manifold, there is a question? No, okay. For the Stiefel manifold, so there is once we have a concrete instance of a manifold, we have an explicit expression for the projection, and the projection is given by this. Okay, just for saying there is an explicit expression. And nabla of f of x is the Euclidean gradient of f capital X. So the loss function or the cost function or the objective function, it's always the same thing. So for example, if f of x is equal to this expression, which is exactly the expression that we saw at the beginning from the KPCA problem, one has that the Euclidean gradient of this expression is minus ax. Okay, so this is just some matrix or vector calculus. Okay, for which well, symbolic matrix and vector calculus, there are many references. The ones that I used in my research is the so-called matrix cookbook, and then there is a nice website that computes symbolic derivatives of expressions with vectors and matrices, so without even using like Mathematica or some other software, which is matrixcalculus.org. But now in software packages, very often people have implemented automatic differentiation. So now sometimes one doesn't even need to compute these symbolic derivatives beforehand. So the reason why I was doing this a lot, computing derivatives like of matrix formulas, because I was using an optimization package which is called manopt. I will mention it again later, which asks you to provide the explicit expression of the derivative of the loss function. Okay, so that's why I also brought this here, and also to give you a concrete example that, okay, so again, the Riemannian gradient is given by a projection onto the tangent space of the Euclidean gradient. Okay, and then the last tool, and very important for this paper, for both the algorithm itself and for the analysis of the convergence, is the parallel transport. So the parallel transport is used to define the Lipschitz condition for the Riemannian gradients, and it is the tool that is used to prove convergence by these authors. So it looks, on the sphere, it looks like something like this. So the name already says a bit what it is. So given a Riemannian manifold and 2 points, x and y, the parallel transport is a linear operator from the tangent space to the manifold at x to the tangent space to the manifold at y. And it is a linear operator that preserves the inner product between tangent vectors and between the two tangent spaces. So for example, to fix our ideas, consider this tangent space, the tangent space at x to the manifold with two vectors which are called psi and zeta. Okay, the yellow psi and the green is zeta. And the property, so the definition of this parallel transport is that, we want to transport these two vectors and preserve the inner product between them. Okay, so when we transport both of them, we have P, the parallel transported psi, so Px to y, so yeah, it's a simplified notation for saying from the tangent space at x to m to the tangent space at y to m of psi, which is again in yellow, and the green one, which is a parallel transported zeta vector. Okay, and now these two vectors have the property that their inner product, so their inner product at the point y is equal to the, let's say, the original inner product of psi and zeta at x. So we'll see later how this is used in the algorithm. But the idea is basically that, so really roughly speaking, high level idea is that, okay, let's say that we have a vector in this tangent space and another vector in this one, and we want to compare them, or actually to do operations between them. So since they live on different tangent space, we cannot do any operation. So we cannot add or subtract them because they do not live in the same vector space. But if we parallel transport the vector to the tangent space, to the same tangent space, then we can perform the operations between vectors. Okay, any questions? Okay, let's go on. Okay, so we basically have everything to have a look at the algorithm. Okay, but before looking specifically at the calculations that are performed on the central server and the local clients, so I made this scheme to show how it works. Let's say the federated learning process, basically, because this is, so it's not just for this specific algorithm then, because for the specific algorithm we will see the calculations. So let's see how it works with 3 local agents. So it's a similar scheme to what I showed at the beginning with n local agents, but now here I just fixed 3, and we assume that we are using we are communicating with all 3 of them. Okay. So let's say that a certain round of the federated learning process, a certain round called t, so small t stands for round t. The central server sends xt, which is just some information, some matrix, okay, let's say it's a matrix, to the local agents, which receive this information and they perform some calculations locally, okay, which I highlighted with this kind of sun around each local agent. So they do, each one does its own calculation and then sends the, let's say, the information, the matrix that they computed back to the central server. And then at this point, the central server performs some calculations, which is called like aggregation of the data or consensus step, and sends it back the new iterate xt plus 1, so x at the round t plus 1 to the local agents, and then it starts again the process. Yeah.
So you're using x here, but as far as I know, this is a sort of, for example, a parameters of a model rather than the original data point, right? Because I mean, I'm trying to distinguish a original data point and a parameter of the model.
Yeah.
The one you are communicating between local and
It has already done some calculations, so it could be like an orthonormal matrix, and is sent to the local agents, and then each local agent performs in each client an optimization process.
Yeah, I agree. I just think maybe this x is a little bit confusing because this looks like it's a data point.
No.
But actually, this is
It's the variable. It's the optimization variable.
So
Yeah.
Oh, I'm sorry. You're right. So you are minimizing them.
Yeah. It's the optimization iterate at a certain time t or t plus 1, and then we have this iterate. Yeah.
Sorry about that.
Yeah. Sorry if it was not clear. There are too many. Maybe there are too many x's around, because also here. So, okay. So we look at the 2 operations now. The calculations that are done on the central server first, which is called aggregation on the central server, and the operations that are done later on the local clients. So how to perform the aggregation on the central server, the so-called consensus step. So this I mentioned before. This is the most common approach also for other types of problems on Riemannian manifolds when we want to find like an average. So we just use the Riemannian center of mass of the points. So it's really like it's the point that minimizes this averaged sum of distances squared or squared distances. So it's the distance. So here the optimization variable is x, and here we have the distance square of this optimization variable that we want to find, that we want to minimize. Well, we want to find the minimizer of this cost function, and xi is the data from each local server. Okay. But yeah, and d is the Riemannian distance, as I said before, and xt plus y is exactly as in the previous scheme, is the next iterate point on the central server. But this is not what they use. So what they use is the so-called tangent space consensus step, which is just so it's really an average in a vector space. Okay, so here you have the logarithm, Riemannian logarithm, and Riemannian exponential. So what is the meaning of this formula is that we basically, let's say, lift all the points that we have on the manifold, we lift them to the tangent space to the manifold at xt, which is the current iterate, let's say, coming from the central server. And then these are just vectors. So we just do a simple average of these vectors. But then what we are interested in, it's not the average vector, but it is the point on the manifold. So we map it back to the manifold. So, and this gives the iterate at the round t plus 1. Okay, so I have a picture on this for concrete example of three points, let's say. So we have x1, let's say x1 from local client 1, x2 and x3. Sorry, but yeah. Okay. So this again is a very unfaithful representation of the Stiefel manifold. Do you have any question? Huh?
So we are just excited about some of our previous work. It's a kind of a sequence.
Okay.
So
Nice.
Very clear.
Okay, so that's nice to hear. So maybe we can have.
We have some, we are integrating some data, also average Stiefel manifold, exactly the same.
Okay.
But at that time, we did not consider federated learning.
Okay.
You can think of that as we want to make average
Yeah.
of points on this Stiefel manifold. Okay, and our iteration, the idea is exactly
It's the same.
Lifting and then
And then
and then average on the tangent and then pull it back.
yeah.
The difference is the exponential map. At that time, you can just mention the logarithm and the exponential map.
Yeah.
Do you have explicit form?
No, so also here, so of course, since I had to, I didn't know exactly the audience, so I tried also to popularize a bit. So I hid some technical details under the carpet. But so this thing, the Riemannian logarithm, in the end, it is not the tool that they use in this paper. So in this paper, they use a tool which is called retraction. The retraction, it's also a map from the tangent space to the manifold, but the property is that basically the retraction is a first order approximation to the logarithm or to the exponential. Well, it depends. Okay, so the reason to do this is that implementing in the computer, it's
I mean, in our previous work,
Yeah.
we have analytic form
okay.
for the lifting and retraction, so the computation will be very fast.
Yeah.
Because that's explicit, analytic form.
Okay.
So it's
But
a
was that the
special type.
Stiefel manifold?
Yes. But it's
Because-
very special, but It's a very special.
Similar method, something like this.
It's very similar.
It's a very special lifting.
Ah, but I know this paper.
It's very, it's a specific lifting and specific reduction.
Okay. Yeah. So for the Stiefel manifold, as there is no explicit formula for the logarithm, but there is for the exponential.
Okay.
Yeah. Instead, if we consider the retraction, there are many alternatives and many explicit formulas for the retraction.
We did not use the exponential map.
Okay.
Uh-huh.
Okay. It's another. It can also be just a projection to the manifold.
Yeah, we have some very specific kind.
Okay. Yeah, we can discuss. It can be something to discuss, right? Well, it's nice. Yeah. But yeah, now I remember, so this is the paper I read like 5 or 6 years ago at the beginning of my PhD. That's a paper about integrating multiple sketches on. Yeah, I know. Yeah. So you see what a coincidence. Yeah. Yeah, because I think you were using the Stiefel manifold, right? Yeah. So I think that was the reason why I found this paper at the beginning, because I worked for quite some time on the Stiefel manifold. Okay, yeah. So we can discuss again this. Yeah. So basically, okay. Going back to the slide, this is what we just explained. So like we lift all the points from the local clients to the tangent space. By the way, again, this is really artistic. Let's say the logarithm doesn't look like something like this, because it's like perpendicular. It's not like that unless we do an orthogonal projection. Then yes, but it's not the case of the Riemannian logarithm. So it's just for simplicity, for making a figure, of course. And then once we have all the lifted points here, well, we just do an average. So these are 3, so it's just average of these 3 vectors, okay? And then this point, the yellow point, is mapped back to the manifold, to the Stiefel manifold, and gives you the new iterate. So it's really always this kind of idea. And so the other calculations, so what do we do on the local clients? So on the local clients, we perform the local gradient update. So here the lowercase l indicates a given iterate for the local optimization process, so the optimization process on each client, okay? To distinguish from the XT, because the XT comes from the central server, okay? And what do we do? So here it's where it comes in the parallel transport, because now, if you look at what is inside the exponential in this expression, okay, let's forget for a moment this is just a scalar, is the step size. So we have the difference between two vectors, okay? Actually, yeah. So one is the Riemannian gradient of the local loss function at xli, which is also represented here in the image. So it is a vector that lives on the tangent space at xli to m. And we want to do the difference with, so the information that we received from the central server at the round t. So let's say with this vector, okay, so this first subtraction, okay, sorry if it's not too clear, but there are many things here. So the first subtraction here, it's between two vectors, actually 2 gradients that live on the same tangent space. So this subtraction can be done without any additional tool. So the whole green quantity is the vector that I indicated here. So this is already grad of the local loss function evaluated at xt minus grad of the global the global objective function, loss function, evaluated at xt. And this is here, at the xt point, of course. But to compare, to do operations, to perform operations between this green vector and the white here, so we need to parallel transport this green vector to the same tangent space here. And this is done with the operator that I introduced above. So it is the yellow part here. So we really transport the green part from the tangent space at xt to the tangent space at xli, okay, in order to perform the subtraction, okay. So this is the local. So this is the operation that is done on each local agent. So what varies is the index I. I denotes the local agent. So there are n of them, let's say in general, and L again it's the index. So let's say the step in the optimization problem where you are currently. Okay. Yeah. Do you have any questions?
Yeah, just a quick question. So what is the green vector in the xt? Can you say that again?
Here?
No, on your graph.
Ah, here?
Oh, yeah, that's right. Yeah. Is that the gradient?
I didn't. So here, sorry, I didn't put the letter because it's too long. It's this one.
The whole thing.
It's the green. Yeah. So these two gradients live on the same tangent space. So let's say I have already done the difference, the subtraction, and this vector, it is this quantity. Yeah. And that's also the reason why here I put like dun 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 in parentheses, because I didn't have enough space to put the whole expression here. Yeah. Okay. Yeah.
So here it involves both the global function f and also the local
Yeah.
fi.
Yeah. Because I think so. My let's say my feeling is that okay, you have the local information, which is the local loss function, but now so it's a kind of comparison. So you look at discrepancy. So you look at the difference, right, between the local loss function at the point that you receive from the central server, and the global loss function. So the one that is given by the sum of all the loss function, and you evaluate at this point. So I think this is the reason why. So you want to use the information that you get from the central server. So that's the reason why they do this difference. Yeah, I think so. But probably, so I didn't look at the original paper of Konechny. I don't know how to read this. But I guess that if this is the manifold extension, probably in this paper where they had the original, let's say, the original Euclidean algorithm, probably there is already an expression similar to this one. So where we do not have the parallel transport and we do not have the Riemannian exponential. Because usually this is the way we extend Euclidean algorithm to Riemannian manifolds. So they are very similar to the Euclidean counterparts, but we have to add the tools like the Riemannian exponential or the parallel transport. Okay. Yeah, so this is the algorithm. Ah, yeah, sure. So the step size, basically all this quantity inside the round parentheses, it gives us a direction for the optimization process. The step size, roughly speaking, gives you the intensity. So, okay, you know that you want to move in this direction, but how much do you want to move? And then to compute this, we usually use some algorithm which is called line search in optimization. Yeah, but this would take us on another, like another topic. But let's say, just say there is a helper algorithm that computes this step, okay? And that is the direction, and that is the intensity that you take.
So why not just compute the normal bits?
Why just not compute?
These are like vectors on tangent space, right?
Yeah.
So why don't you just compute the normal value? You just want the intensity of it.
The normal value? What?
They are vectors, right? So they can
Yeah.
compute the normal on tangent space.
Ah, yeah, I mean,
Why not?
because maybe if you move, so you mean without putting 1 to this step size and just moving with,
I just wondered because you just tried to tell me that the step size is the measurement of trying to tell us how intense it is.
yeah,
to, like,
because, yeah,
change. So I was
Yeah.
thinking that the most intuitive thing that I can think of that actually tells you intensity as a measurement would be snow. Isn't it?
would be,
Would be snow. Would it not?
because it might be too much for the I mean, so it really gives you just the direction where you have to move. But it might be the step that you take if you use the norm of the gradient. So like if basically what you're saying, if you choose eta equal to 1, yeah, so it could be too much for the optimization process. Okay, so it's a kind of technicality in optimization process. So you often use this line search. Yeah. You can also take take it equal to 1. It's a possibility. So the fact that it can be different from 1 allows us more flexibility maybe in the algorithm. Okay. Yeah. So the algorithm looks like this. The Riemannian federated SVRG. It has 3 inner loops. So, okay, well, before looking at that, let's say, okay, the inputs are n is the number of local agents. K is basically, yeah, so the authors here, they consider also, let's say they consider the possibility that we do not take all the n local agents, but we only take a subset of them, a k. So k is usually much less than n, okay? Capital T is the total number of rounds in the federated learning process. Eta I are the step sizes in the local gradient updates, and tau I is the number of local gradient steps, okay, in the local optimization processes. That's why there is always the index I, so it can be different for each agent, okay. So there are 3 nested loops. The first one, of course, is across the number of federated learning rounds. So from 0 to total number t, well, okay, t minus 1, because okay, indices start from 0. So what the authors decide to do in designing this algorithm is they take a subset of the local agents, so they do not use them all at the same time, okay? So as I was saying, with the subset of k local agents. So that's why then in their analysis there is also some, let's say in the convergence results there is also some randomness and convergence in expectation, okay? Then for each agent, for each local agent, as we saw from the scheme before, each local agent receives xt from the central server. It is renamed x0i, so again I, because it's the ith local agent. 0 is the index L. So now in the, let's say, the innermost loop, we have L that goes from 0 to tau I minus 1. Okay, so the total number of local steps. And the local steps is exactly the formula that I just showed in the previous slide. And then once every local agent has done its own optimization process, it sends the information to the central server, and this author considered two options. So I didn't devote too much time in this presentation. So okay, to this thing that they have two options, because okay, there is not time for everything, and I think it's already 5. So, but okay, so option 1 is, let's say, the standard. I would say the standard thing that we would do in deterministic optimization. So the X, the data that we send to the central server, it is the last iterate from the local optimization process, right? Because they are so we arrive so we arrive at tau I with this formula. We arrive at tau I, x tau I I. So this is really the last iterate from these local gradient steps, right? And the other option is instead to sample uniformly the data that we send back to the central server from all the set of iterates that we have for that local agent. Okay. Okay, and once we have sent all the information to the central server aggregates the points by the tangent space mean that we saw from the other slide. Okay, this expression. Yeah.
Is the xi in your aggregating the points the same as the x hat I? It's the same. Do you think you use a difference?
Yeah, okay. You're right. So rigorously, this should be x hat.
Okay,
Yeah. This should be x hat, right? Yeah. Thanks. Yeah. So, and for the convergence results, well, okay, there are a lot of like the paper is very short and the appendix is very long compared to the. So the appendix contains all the analysis. I didn't go through it in detail yet because I mean it depends if we will use it or not. But let's say. Generally speaking, they use standard assumptions for optimization on manifolds. So the Lipschitz smoothness, in which in this condition there is again the parallel transport. The completeness of the manifold, as we discussed towards the beginning of the talk. The fact that the sectional curvature is bounded, which is the case for the Stiefel manifold and for the sphere, of course. So these are all assumptions that are satisfied again for the type of manifolds that they consider. And this is an additional assumption. So geodesically convex, it gives a stronger convergence result if we assume that the objective function is geodesically convex. To summarize, they give 3 convergence results in different scenarios. So the first one is theorem 7 in the paper, is for tau I equal to 1. So it means in each local agent at each round, we just take one local gradient step. So that formula, we just apply it once, the formula we saw before. Theorem 8 considers more than one local gradient step. And then the last result is for a geodesically convex objective function, so they can obtain, let's say, a stronger convergence result. Yeah, so, okay, so there are still numerical experiments. It's the last part of the paper. So what they did for so they first consider, let's say, artificial data, as I was mentioning before, they're just like basically randomly generated orthonormal matrices, and then they construct the covariance matrix, and they compare their algorithm to the manifold extension of two existing algorithms, which I also mentioned before, I think. So FedProx and FedAVG. And here in the slides, I just give the results for the KPCA. So they also have other experiments in the paper. And they test the algorithms with different number of agents, with n going from 50 to 1,000. So it's the one we can see here. So the columns. So we have n goes from 50 to 1,000, and k, as I said before, k is the subset of local agents that we use at every round, and it's n over 10, as you can see also from here. Okay. And for the dimension of the, let's say, of the optimization variable, so the matrix. So these are the dimension of are the parameters of the Stiefel manifold. So in this case, they consider the Stiefel manifold 205. Okay. And the monitor quantities. So the first one is, as I said before, is very classical. So we monitor the norm of the Riemannian gradient. In this case, we desire it to be pushed to 0. Or to the machine epsilon, let's say, machine accuracy. And they consider also the principal angle between xt, which is the iterate at round t, and x star, which is the exact solution, may be computed with some other method, which they can do because, okay, it's not such a big problem. And I mean, yeah, okay, we use that as a reference solution, as if it were the exact solution, let's say. And yeah, the reason for doing this, the thing with the principal angles is because, so basically, so now these two objects are matrices, are orthonormal matrices, so we can consider that their columns, they span a vector space. So we want to see if this, if there is some kind of angle between these two hyperplanes, between these two vector spaces. So we also want this angle to go to 0. Okay. Because we might have I mean, okay, I think you know this, but we might have like a situation in which if we do the direct subtraction of xt and x star, and we consider the norm, we might have a situation in which, well, their columns, they actually span the same vector space, but since maybe because of some signs, when we do the subtraction, we do not get like norm close to 0. Okay. So that's the reason for considering the angle. And what I could, so now this is my maybe my observations, because I think it's a really nice preprint, but I'm really surprised by there is no discussion of the numerical experiments. Really, you can look at it. And they didn't write basically anything. So they did a lot of nice experiments, but there is no discussion. So, okay, so what can we see from here? Well, this they say, of course, that so with respect to the plain straightforward extensions of the existing algorithms, their algorithm, the green curve, performs much better. Okay, so the two straightforward extensions of FedProx and FedAVG, they stagnate very soon. You can see from here. Well, they are really bad, really bad. And while their algorithm converges, and it can actually push to, well, to 0, to an arbitrary precision, let's say, the norm of the gradient. But so what we see is that if we increase the number of local agents, well, this is not so good anymore at the same number of round of communications, which was taken equal to 600, right? Because here you see you have 10 to the minus 2, Then you have 10 to the minus 1 for n equal to 100. 10 to the minus 1. Here you have 10, 0, which is, I mean, I don't know. I'm a bit surprised that they stopped the simulation here. I really don't know why. I think the reason is just that, okay, I mean, if they take many more iterations, they can also show that they can reduce the norm more than this. But it's a bit surprising to me to put in a, maybe it's just myself, I'm not used to this kind of problem. So it's a bit surprising for me to see in a convergence plot, especially for the norm of the gradient in the order of 1. Because usually what we want to see is that we can push the norm of the gradient to the machine precision, right? So I don't know. If you have any ideas about this, please share. They actually do that. Well, also this other experiment is to test the effect of the number of local gradient steps tau. It's quite similar, the results. So you can see that their algorithm performs much better than the other two natural extensions to manifold. A small critic also. I mean, it's difficult to compare these plots, right? Because, so here they stopped at 500. And here they stop at 300. And here they stop at 200. So if I want to see, so either, yeah, it would be simpler to look at them if they are on the same plot, maybe. And again, there is no discussion for the impact of tau. They just say, for any tau, we observe good performance of our RFedSVRG. And again, yeah, that's what I just said. I'm really surprised by such low accuracy in absolute terms, in the sense that, if you look here, it's 10 to the power of 0. So again, I don't know. Maybe just increase the number of iterations, we can push it. We can obtain more accurate results. So again, here I'm really open to discussion. Instead, for the experiments with real data, okay, here we see something which is more standard, let's say, because so the experiments are done always KPCA with ARIS and WINE data sets, apparently some quite well-established data sets 25 years ago, almost. So they random partition the data sets into 10 local agents. And at each iteration, they take 5 local agents, okay? And again, so here also, we can compute the, let's say, the exact or the reference solution X star with some other method, compute it directly, and use for comparison, okay? So here, yes, you see that the norm of the Riemannian gradient with their algorithm, always the green line, is pushed to the machine precision. So here's double precision, okay? So this is a nice plot. So this is pushed to machine precision for the ARIS data set, and the same thing is true for the principal angle, okay? So the monitored quantities are the same as in the previous experiment. So the norm of the Riemannian gradient and the principal angle between xt and x star. And the same, similar thing is true for this other data set. Yeah, I mean, here the accuracy is more satisfactory. We do not see the plateau at machine precision, but we can see that this is a nice line. So just performing more iterations, we can probably see the plateau at machine precision. Oops, sorry. Yeah, okay. And these are final experiments are similar. So it's again the KPCA with the MNIST data set. I think you know this data set much better than me. So this is a quite big data set. And in these experiments, they considered 100 local agents and 200 local agents. So again, we can see that they can, we can reduce the norm of the Riemannian gradient and of the principal angle, where the other methods are really bad. They stagnate really soon. And again, the same consideration. So, for more accuracy, more iterations, and we can see that for a bigger number of local agents, so the accuracy is not so good. So we really need many more communication rounds in the federated learning process. Yeah. So this is the last slide of my presentation. So to sum up, in the papers, the authors proposed a new effective algorithm for federated learning on Riemannian manifolds. There are also theoretical results on convergence, which we didn't really see here. But okay, I mean, it's already a lot of things. Numerical experiments, we just saw them. And then they also leave some open directions for future research, such as designing algorithms with a lower communication cost for the network, with better scalability and considering sparse solutions. And so you can find these slides at this address if you want. And thank you again for the attention. Sorry I went a bit over time, but there were also in-talk questions, so I hope it's fine. Yeah, thanks.